Hi, today we're going to talk about our project Predicting MBTI with Text Samples. The Myers-Briggs Type Indicator is one of the most popular personality tests. It evaluates individuals based on 4 dimensions of personality. Based on the results of the test, a person is assigned one of 2 letters for each dimension, resulting in 16 distinct types, such as ENTJ. Despite its widespread popularity, its usefulness has been put into question by many. By training various models to guess a person's result based on a sample of text written by them, we can gain insight into whether personality type has a meaningful correlation to a person's writing style. We used a Kaggle dataset containing over 8,600 rows. Each row is a collection of posts by a user to the Personality Cafe forum, labeled with their personality type. There are 2 main issues with this dataset. Firstly, the content posted in this forum may not reflect how people talk or write in general, and secondly, the distribution of personality types is different from the real-world distribution. Here are the 4 models we tried. To evaluate performance, we assessed the accuracy of each of the 4 individual dimensions when possible, but the main measure we used was the accuracy of predicting the exact personality type. By randomly guessing, we would expect an accuracy of 6.25%, and a trivial model which always guesses INFP, the most common type, would get an accuracy of 21%. These give us some good thresholds for what we would expect a successful model should be able to beat. The first model is binomial naive Bayes. The data flows through preprocessing and binary vectorization before being passed to the model. Interestingly, the model predicting an exact type seemed to always guess IN for the first 2 letters, as they're the most common in the data, and was more successful overall. However, the 4 binary predictor model may have been more accurate on a per dimension basis, while sacrificing overall accuracy. Here we can see the effects of adding smoothing and changing the maximum feature parameter for the count vectorizer function. The next model is SVM. We trained 1 model for each dimension, with each model having 1 letter set to -1 and the other set to +1. First, we did some pre-processing on the data to clean up things like punctuation and converting to lowercase. Then we vectorized the data using the TF-IDF vectorizer, which is similar to count vectorizer, but it also considers how often the same words appear in other documents. We treated this as a soft margin problem and used random search CV to tune various hyperparameters. We ended up with a linear kernel function, setting the slack variable c to 3 and a small gamma value of 0.01. The resulting model had a test accuracy of 55.6%.
The next model is a dense neural network with 5 layers. The model takes one user's collection of posts as an input and tries to classify the user's whole personality at once, rather than letter by letter. The posts are tokenized and then fed into the model, going through each of the layers sequentially. In order to extract meaning from the tokenized data, the first layer is an embedding layer. Then, a global average pooling layer reduces the dimension, which is then fed into the fully connected dense layers. The last layer uses a softmax activation, which outputs a probability distribution for the post over each of the 16 different personality types. The metric used for performance here was accuracy, and after just 9 epochs, the model was able to classify the test data with 50.2% accuracy. We found that the performance improved when the number of nodes in successive layers followed a decreasing geometric progression. When trained for more than 10 epochs, the performance started to decrease. This happened because the model started to overfit to the training data, failing to generalize to a more varied vocabulary. Here, an interesting finding is that when considering inputs from the more agreeable, feeling-based personalities, their posts used words like feel, helping, our, and we, which were indicative of their personality type.
We also tried training 4 neural networks for each of the 4 dimensions of personality. Similar to the naive Bayes model, this method wasn't as successful at predicting the exact personality. We decided to take a closer look into interpreting this model. Here we can see an example of what words the model associated with introversion versus extroversion. Highlighted in blue, we can see words like think, concept, and mind being associated with introversion, whereas words in orange like people, entertaining, and surprises are associated with extroversion, which makes a lot of sense. We also tried deleting certain words and observing the effect it had on the model's prediction. For example, removing the word not made the model more confident that the post was extroverted, and by removing some of the orange words, we can make the model think the post was more introverted.
One of our models is a recurrent neural network. It's 4 models in total that is used to classify each of the axes of the MBTI. The important parts of the flow of data is that the training data is always balanced and the posts are tokenized for a simpler representation. The labels are also converted so that we can test each of the 4 dimensions individually. The process data then gets set into 3 algorithms using the same models. For all of our models, we use accuracy to measure performance. The recurrent neural network did not perform well. It had a 3% accuracy for predicting an exact personality. We removed some common words that appeared in each personality and measured the performance. We also removed the 2 unique words from each personality in each axis. Both these actions resulted in an increase in accuracy for one of the axes, and they both doubled the accuracy of predicting an exact personality. From these results, we can conclude that removing some common words can increase the accuracy and that removing words that are unique to a personality does not always decrease the accuracy. Since the recurrent neural network performed worse than the dense neural network, it could be the case that the order of the words and the grammar is not a strong feature when predicting a personality from our dataset. All the results from the permutation test indicate that the null hypothesis must be accepted. In other words, the recurrent neural network is not able to find the relationship between the post and personalities. The recurrent neural network performed worse than chance.
Here are the results from all of our models. Overall, the SVM was the most successful model, but the naive Bayes and the dense neural networks were also quite accurate. It's also worth noting that the models predicting the full label were more accurate than their counterparts. We did find a larger dataset that was derived from Reddit posts, but due to time constraints, we were unable to train and test all the models with it. So some next steps in the future would include trying the existing models with the new dataset, as well as using more parameters for models such as the RNN to see if we could make them more successful. Thanks for watching.